guys, welcome to this tutorial, and we're going to be going over ionic versus covalent bonds. So let's first review some basic concepts on bonds. Bonds are formed through chemical forces which hold atoms together. This allows for the creation of compounds and molecules. These chemical bonds will possess strong intermolecular interactions, and these interactions are known as covalent or ionic. Lastly, bonds are made from valence electrons on the atoms. One important rule to remember surrounding bond formation is the octet rule, which states that an atom is most stable when it's bonded to 8 electrons in its valence shell. Therefore, we can predict that the majority of atoms want to be the most stable form. So some exceptions of this rule are beryllium and boron. We have learned up until now that ionic bonds involve a complete transfer of electrons, whereas covalent bonds involve sharing of electron pairs. From this, we were able to differentiate properties that pertain to each bond type. Covalent bonds are formed between two nonmetals and will share valence electrons. They can be gases, liquids, or solids and have a low polarity and low melting and boiling points. Additionally, covalent bonds do not conduct electricity, and examples of this are methane. Additionally, ionic bonds, on the other hand, are formed between a metal and a nonmetal. In this type of bond, the metal will lose electrons, whereas the nonmetal will gain an electron, giving both charges that increase their stability. Ionic bonds have high polarity, and therefore they have high melting and boiling points, as well as they can conduct electricity, especially when dissolved in water. Examples of this type of bond can be seen as sodium chloride. So, more than just two types. So this brings us to first year chemistry, and the idea that ionic and covalent bonds are either or is incorrect. So chemical bonds are actually on a continuum between 100% ionic and 100% covalent. The properties that allow for this spectrum are electronegativity and ionization energy. So there we go. This is the nonpolar covalent, polar covalent, and ionic bonds. Most compounds have polar covalent bonds where the electrons are shared unequally between the bonded atom. The atom that is more electronegative will hold onto its electrons more tight and therefore pull neighboring electrons closer as well. This asymmetrical charge distribution will lead to dipole moment, which is defined as the product of the partial charge and the radius. The dipole will often increase as electronegativity increases. A cool fact is that the strength is known as the dipole moment, and it's expressed in Deeb units with respect to the Dutch chemist Peter Deeb. So the measurement of dipole moments can be very useful in determining the shapes of molecules, a characteristic that we can touch on at the end of this tutorial. An electrostatic potential map is able to give information on the distribution of electron charge within a molecule. An arbitrary rainbow scheme is used to show the dispersion of electrons, with dark blue being the most positive electrostatic potential and red being the least positive electrostatic potential and has the lowest energy. So in the diagram, blue has a positive dipole, we can draw that here, and red has a negative dipole, like that. So there are many properties that exist with bonds. But two very important properties are electronegativity and ionization energy. First, electronegativity is an atom's ability to compete for electrons with other atoms bonded to it, and is a measure of how tightly an atom attracts electrons towards itself. The stronger an atom attracts electrons, the larger its electronegativity. Secondly, ionization energy is based on the difference in electronegativity between atoms and gives us an idea of the polarity in the bond. Polarity comes from the unequal sharing of electrons between two atoms. If electrons are displaced towards the more nonmetallic element, this would be referred to as a polar covalent bond. This polarity will lead to an unequal sharing of charge and cause a dipole, which is a partial negative charge on the more nonmetallic element and a correspondingly partial positive charge on the other atom. The electronegativity values allow insight into the polar character of covalent bonds due to their electronegativity difference. If the electronegativity difference between two atoms is small, then the bond is covalent, though if the electronegativity difference between the two atoms is large, then the bond is ionic. For intermediate values of electronegativity difference, the bond can be described as polar covalent. We can see this in the graph presented on the right of the slide. On the left of the slide, sorry. At the very left of the graph, we can see that covalent bonds, and this is because the electronegativity difference is small. And as we increase right towards the slide this way, we can see increasing ionic character as electronegativity difference increases. And this is our intermediate value, and over here we have our ionic bond types. So an element with high ionization energy and electron affinity that is large and negative will have a much larger electronegativity. So Linus Pauling devised that the lower the electronegativity is, the more metallic the elements seem to be. Therefore, on the periodic table, we'll see increasing electronegativity as you go from left to right and decreasing electronegativity as you go from top to bottom. Along these lines, ionization follows the same pattern, though atomic radius will follow opposite patterns, decreasing from left to right and increasing from top to bottom. So you can find the electronegativity on your periodic table. If you're not sure where, you can look at the legend at the top, and it will most likely be underneath the atomic mass. But if you can't find it, I've included this handy dandy periodic table with the electronegativities, and you can use this for questions that you're doing if necessary. So to find the electronegativity difference, we must first look at the electronegativities of hydrogen and fluoride. So from looking on my periodic table, I found the electronegativity of hydrogen is 2.1 and fluoride is 4.0. So to get the electronegativity, we subtract the larger electronegativity by the smaller one, difference, and then we get 1.9 is the electronegativity difference. Now, what type of bond do you expect will occur between these two atoms? If you guessed ionic, you are technically correct according to our previous knowledge, but it just so happens that hydrogen fluoride is one of the few exceptions to our general guide. Hydrogen fluoride is actually categorized as a polar covalent bond type, although its electronegativity is somewhat in a gray area. Some reasons for this go back to our previous categorizations of ionic and covalent bonds. As you may have noticed, hydrogen is non-metallic, and hydrogen is also a nonmetal. Therefore, when it forms with fluoride, it's going to form a covalent bond. The hydrogen fluoride bonds are a virtue of polar covalent bonds, and this occurs as electrons are displaced towards the more electronegative fluorine atoms. Fluorine pulls the electrons in the bond closer, which forms a partial negative charge, and this results in the hydrogen atom having a partial positive charge. Think back to the electrostatic potential map, and remember how the electrons in hydrogen fluoride were attracted to the more electronegative fluorine. Great. So now that we know a little bit more about ionic, covalent, and polar covalent bond types, let's do some example questions. Here we'll be categorizing bond types, and you can use the electronegativity values that you can find on your periodic table. Hint is to look at the legend if you don't know where it is, or you can rewind this video and go to the periodic table with the electronegativity values listed. I'll pause it here and go ahead and do the questions if you can. Okay, so you should have the same or similar answers to mine. At times, the electronegativity values may differ slightly based on which source you're collecting from, but all categorizations should be the same. Sodium chloride and potassium chloride are ionic, as this occurs between a nonmetal and a metal, and has a high electronegativity difference. Then, carbon monoxide, hydrogen chloride, and carbon chloride are all polar covalent, as they are nonmetals, which share electrons, but have a dipole that the difference between their electronegativities is slightly larger. And carbon and hydrogen is covalent, as it has a electronegativity difference of 0.4, and it's between two nonmetals. To extend off this idea of bond types, I'd like to use the example of carbon tetrachloride. So in this example, you have the carbon chloride bonds, which in our previous examples we identified were polar, but the molecule itself is actually nonpolar, and this is because the dipole moments are actually vectors, and to determine the molecular shape of carbon tetrachloride, the charge and the magnitude of each dipole moment must be added to determine the net movement. So in the case of carbon tetrachloride, the net dipole moment is 0, and therefore it's not polar. This pertains to the VSEPR theory, which while not being the focus of this tutorial, is an important concept that extends off of our idea of bond types. Vesper theory assumes that each atom in a molecule achieves geometry to minimize repulsion in electrons in the valence shell. This model can be used to predict the shape of molecules in polyatomic ions. Carbon-tested chloride makes a tetrahedral, and when drawing the dipoles of each bond type, we're able to see that the dipole moment cancels out, making the molecules nonpolar, even though it contains polar covalent bond types. So to do a quick rundown of what we did in this tutorial, we reviewed the 3 types of bonds, covalent, polar covalent, and ionic, as well as the properties that allow for these different types of bonds. And we also went over how to differentiate these types of bonds using electronegativity differences. A key point from this tutorial is that while there are various exceptions to our classifications of bond types, such as hydrogen fluoride, you can use your knowledge about bond properties to identify the bond nevertheless. So overall, remember that bond types exist on a continuum between 100% ionic and 100% covalent, and that the intermediates in between that are polar covalent compounds that have dipole charges. Thank you for listening, and I hope you have a great day.